All right, so I think I can see it's happening, and I'm just checking on YouTube, make sure that's also getting the stream. Yep, so looks like we are all good here. All right, so this is week 2. So welcome to week 2 of back to in-person teaching. I wrote a little announcement, just to remind people because I want you guys to be aware of this is where things are starting to pick up. So if you did not have a chance to read the announcement, we're gonna I'll just kind of briefly go over, okay, because you guys can read the detail. So this is where we will start to introduce concepts that are more abstract, which means it's not going to be enough just to be in class and listen to me during class. Some people may need some time to study before class. Some people may need more time to study after class. But during class, I think it is really important to take notes and also to participate. If you guys say, I'm not really sure what that symbol is representing, just let me know, okay? Just raise your hand or frown at me in a very funny way. It's like that, you know. Doesn't have to be verbal. And most of your fellow students are not looking backwards to see what your facial expression is. So don't worry about people saying, oh, that guy's asking questions, because most people are probably asking the same question. It's just that no one wants to ask. Yep, go ahead.
It does seem to be saving the stuff.
It does. Okay, very good. But don't count on it. That's what I'm saying. Don't count on it. Because other students who use the same workstation, if you can save it, the other students can remove it. So don't count on it. Okay? Just use a thumb drive, make sure that you have your own copy. All right, so getting back to here. So this is when we start to kind of get into topics that can be that can take a little bit more time to sink in, and take more time to really understand. I say this because the first exam, in my previous semesters, despite me not using new types of questions, it would appear to me a lot of people are still not understanding the concept, starting with what I'm going to be introducing later today. So just want to give you guys a heads up because I think it's kind of important. Once now that I know it, okay, I think it is important to let you guys know what to expect at this point. All right, so that said, we are going back to the module that I started last Thursday. So I hope you guys got some time to kind of review the material from last Thursday, not last Thursday, it's last Wednesday for you guys. So 4 days ago, okay? Just to kind of go over the concepts, just to go over the process, just to go over what we did in class in terms of base conversion, okay? Because it's really important to do all that before class today so that your mind is already having all the context necessary to learn new things that are basically stacking on top of what we have already introduced last Wednesday. All right, so I am skipping a bunch of content because the first part here really is just an explanation. Maybe I'll just start with this part here. So this is a number in base 10 because usually if I don't specify the base, it is just assumed to be in base 10. So we are looking at a number of 16.375 as a base 10 number. So eventually we boil it down to 1.10 to the power of 1 plus 6 times 10 to the power of 0 plus 3 times 10 to the power of negative 1 and so on, because what each digit is saying is telling you the quantity of each power of 10. That is basically what a number is. So that is why, also why we can now generalize. If you have a number where d subscript I is the ith digit, or digit I, okay, however you want to call that is fine. But what is digit I? Digit I is basically the digit that is giving you the quantity of whatever base to the power of I itself. So the value represented by a number is now d0 times 10 to the power of 0 if the number is in base 10, because d0 is digit 0. It is telling you the quantity of how many 10 to the power of zeros, basically ones, do we have, and so on. So you can see how this can go in both directions. So you can have d1 times 10 to the power of 1, and then d negative 1 times 10 to the power of negative 1, and so on. So it expands on both sides with the decimal point indicating where the power of 0 is located. Okay, so that's basically what the point is. It's really just telling you, because without the point, you don't know where to start. Okay, you have no idea, where is d0. So the point is basically saying whatever is immediately to the right-hand side of the point is where where d0 is located. That's it. Okay, it's just a little marker or bookmark to help you remember where it's supposed to go. So if you generalize and say I have an infinite, base 10 number, because remember, on the left-hand side, the more significant digits, even though all I want to represent is 16.375, I can still say, well, there are zeros of thousands, zeros of 10,000s, zeros of 100,000s, and so on. So you can basically pad zeros on the left-hand side, until you run out of ink, okay, or paper, okay, and it still won't change the value being represented by the number. The same thing also applies to the right-hand side. So if you pad another 0 here, all it is saying is we don't have any 10,000, of in this particular value. But then you can also append as many zeros as you want on the right-hand side because there are none of those powers of 10s. Are we doing okay so far? Okay. So the way to say the value represented by a base 10 number is now a summation. Are we all familiar with the sigma notation, or should I explain that first?
Is it sort of like a loop, kind of?
Yeah, it's a loop of summation. I can give you kind of like a very brief explanation in quote-unquote code way. So I'll get back to that one. So sigma is just summation, where I is an index in this case. So all I'm saying is if I goes from negative infinity as an integer to positive infinity as an integer, then the summation of the product of di times 10 to the power of I, that summation, that gigantic, huge addition, the summation, is the value being represented by a base 10 number in this case. So do we have any questions about the notation? I will explain the sigma in just a little bit, but I just want to make sure that D0 is understood, what it is representing, the D subscript stuff. Because today's lab is going to refer to that. Are we good so far? Okay. All right. So let me see if I can explain the sigma notation in a general way. And let's see, there we go. So 0829. All right. I'm gonna use Markdown. So later on, if you guys want to, I can convert this into a PDF or an HTML document. But right now it's just C code. So if I want to express summation, okay, so the math notation of summation in LaTeX is just dollar sign, backslash sum, and this is the subscript part. I equals I'll just say constant A to constant B of some kind of function of I. So we want to express what that value is. I will show you how it's rendered in just a little bit. But the C code corresponding to this is really just for int I, beginning with value A, I is less than or equal to B, plus I, which means for each iteration of the loop, I is incremented by 1. And I need another value up here, so I'm going to say double sum, starting with a value of 0. And then inside the loop, all I'm doing is to say sum plus equal to f of I. So these two are basically representing the same thing. So if you're looking at this and go like, I have no idea what that dollar sign thing is doing, let me see if I can render it right now so you can see it. I should probably reinstall one of the modules that will allow me to render in real time. But since I don't have it, I'm just going to need to do the rendering in. Oh, okay, I can show you all this. This may be useful. So let me see if I can find an online mark down to HTML converter, maybe. All right, so there we go. Okay. Okay, so this is nice because now I can just remove everything on this side, and I can now paste the entire content of this file. So that's going to be cat22 da 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 2 xclip. I think that should do it, but we'll see. And then do a paste. No, doesn't do it. Okay, I did not do that correctly. All right, so let's give that one more try. There we go.
Is that a command line to manipulate the clipboard?
Yeah,
Okay.
yeah, to put things into the clipboard. Unfortunately, it does not render the math stuff correctly. Alrighty, fine. We'll pick another one that can do the math stuff. And that's math jacks. I'm trying to look for one that is that can give me real-time rendering. Okay, maybe not that easy. Let me see if I can do this. Pandoc-I to do. Rendering as text. Okay. All right, fine. I'm not gonna waste too much time. Let me show you what it should be rendered as. Yep, these are not web platforms that can do it. So. Right, so here you have the C code. What I'm going to do is to write out the math equation in the sigma notation. So the sigma notation is for summation, because sigma starts with S, and then there's also pi that stands for product. But in this case, I goes from A, which is just some kind of integer. It can be negative, can be positive, and then B is supposed to be at least A, and then this is f of I. So this is the expression that is computed by this C code here. So we do okay so far in terms of the notation in math and the actual logic of how it is computed. Yep.
F of I, what is that?
F of I is just some function.
Okay.
Yep. So it's just some function that depends on I.
And that value is just getting added to each, like the running total
Yep.
sum.
Yep. So if you want to kind of spell it out, in a very casual way, so this thing is just f of a plus f of a plus 1 plus f of a plus 2, blah, 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 and then all the way to f of b minus 1 plus f of b. So a is the first value where you use it to compute f, and then b is the last value for the entire quote-unquote series. All right. But the sigma notation is really useful. We are going to use it quite a bit in this class. So it is important to understand that notation. And this would be a good time if you want to kind of jot down, like the timestamp. And this is when I start to talk about the sigma notation. So this way, if you ever need to go back to kind of trace back, okay, what does that mean again? You can at least trace back to the video. Unfortunately, what I wrote on the whiteboard is not going to be captured, simply because I could not figure out the easy way to convert from Markdown to HTML. Are we good so far? Okay, so the sigma notation is fine. All right. So now the question is, how do we convert so the next thing to generalize, if you look at this particular expression, it has a constant of 10. And that's because you're assuming that we're dealing with base 10 numbers. So if you say, but what about base 5? What about base 7? What about base 2? And so on, you're just changing the 10 to whatever base you're choosing to use. So the more general version of this, so if you just compare the two expressions, comparing this one versus this one down here, the only difference is the 10 is now generalized to B, which means, if you just want to use base 2, then B becomes 2. If you want to use base 5, then B becomes 5. So regardless of which base you want to use, as long as you have a number in that base, I'm giving you a way to figure out what is the value being represented. So are we good so far? Given a number, you can figure out what value is being represented. Is that okay? All right. So this is right before section 5. That's also another way you can use, you can take notes, is to basically say, okay, where is this located? Which module are we talking about? This is module 02H2, which is about base conversion, and we are right before section 5 in that particular module. All right, so now we want to do the other way around. In other words, if I give you B and I want to convert that value into a number in a particular base, what do we do? What can we do to get to the number from the value? So I'm going to give myself a really kind of random example, okay? So I will give myself an example, and this time I am going to type, because I think this time, just using plain text, should be fine. So I will use plain text. At the end of the class, I can convert this, using a batch process so that you guys can have a copy of this. All right, so what I want to do is to look at the value that we normally know as 1091, as a base 10 number. And I want to convert this to a base 7 number. And once again, the base 7 number, I'm going to use D2, D1, and then D0 without the suffix, because it's harder to use suffix in the case of a just plain text editor. So this means I need to figure out what is D0, which is representing the number of ones. I need to figure out what is D1, which is the number of sevens. D2 would be the number of 49s. And I think we need one more digit here, D3, which is the number of 343s, because that is 49 times 7, which is 7 to the power of 3. So last time, we went through a process to kind of just say division, right? So you divide 1091 by 343, that would become D3. Okay, but that means you kind of have to do it in a particular order. So what I'm going to do now is to give you a way to compute, just isolate D1 all by itself, okay? I don't care about the other digits, just D1. Don't ask me why, but that's what I want to do. I want to know the number of sevens in this entire number without having to know the other ones, okay? So now I want to say, okay, what about D1? I just want to know D1. What is that going to be? So the first thing you need to know is, okay, what does it mean? What is the meaning of D1? It is telling us the quantity or the number of 7 to the power of 1, because digit 1 is the quantity of whatever base raised to the power of 1. Okay, so that doesn't seem too hard, right? Because now we can just say, well, okay, that's just 1091 divided by 7 to the power of 1. So in this class, at least for now, I'm going to use the caret symbol to represent to the power of. If you guys prefer, I can just use a power function as well, but either way is fine. But this is not going to work, because each digit in base 7 can only range from 0 to 6, exactly. So in base 10, we only have a single digit to represent from 0 to 9. So in base 7, we only have digits to represent from 0 to 6. But this value, if you just look at this one here, is not going to be 6. This is going to be way more than 6. So what are we going to do?
Kind of lost.
All right. So let's just figure this value out, okay? If you are to figure out this value, I'm going to use a command line a calculator. We have 1091 divided by 7, and that turned out to be 155. But that doesn't make sense because 155 doesn't make sense to be a single digit in base 7 because we know each single digit in base 7 can only range from 0 to 6. Okay? So now the question is, what am I going to do with 155 to get me the one single digit that I need? Because 155 is not a digit in base 7.
Do you go down to the lower like increment? Because if you need to get to 6, but you only go by 7s, do you go to like 7 raised to the -1 or like 7 raised to the -2?
Nope. There's one particular operator that is really helpful. It's kind of like the evil twin of integer division in C++. Mod, exactly. So mod is going to give you the remainder after a division. So if instead of focusing on the quotient, we can now ask, okay, what about the remainder of this particular division? I'm not sure whether this is going to work in this calculator because I'm not sure whether it can. Oh, it does. Okay, fine. So it has a remainder of 6. So now I can isolate and say, aha, 6 is the answer to that question. So if I go back to the document that I had earlier, now I can say this number, this entire thing, okay, I already got parentheses around it, it's going to be more than, can potentially be more than 6. So now we just have to say, if I just mod it with 7, then I guarantee to end up with an integer that is from 0 to 6. But there's one more thing about this that is kind of like, but Tack, I'm not sure this is going to work. Because I'm relying on the fact that this slash is meaning integer division, which means it's not going to give you a floating point number. It's not going to give you all the decimal points and whatnot. It's just going to give you the integral portion of the actual division result. But if you're talking to a math professor and you say, well, division is only going to give me the integer part of the result, the professor is going to look at it and go like, no. If you ask me what is 4 divided by 5, it's 0.8. It's not 0. Okay. So that's why we also need to use what we call the floor function to make sure that we end up with an integer before we perform the mod operation. So are we doing okay so far with this process?
You talking about the floor function?
Sure. So I can explain it right here. So the floor function of some random value x is basically the largest integer that is less than or equal to x. That's basically how the floor function is defined. Let's go through a few examples, okay? What if x is 1.3? What is the largest integer that is less than or equal to 1.3? There'll just be 1, right? All right, so let's think about what if x is 17 as an integer.
17.
It'll be 17 itself, right? Okay, so this is the trick one. Okay, this is a tricky case. What about the floor of -0.5? What is the largest integer that is less than or equal to -0.5? -1. -1. Because if you think about the number line, okay, and this is the number line of real numbers, this is 0, this is where -1 is, and where's 0.5? 0.5 is right here, right, between 0 and -1, but we're always looking for the integer that is less than or equal to whatever the value is. 0 is not less than or equal to -0.5, but -1 is. Is that making any sense?
You said the largest integer.
It is the largest integer that is less than or equal to.
Oh.
So -1 is still the right answer because it is the largest integer that is less than, which means it's to the left-hand side of the value that we are concerned about, or equal to. All right? So that means now we have a equation to figure out what is D1, given the value that we want to convert is 1091, and the base that we want to deal with is base 7. Are we doing okay so far with this? All right? Question? No? Okay. So how do we know that TAC is telling you the truth, that this is actually going to work out? Is there a way to double check that this really is the case? How can you double check based on what you have already understood up to this point and say, okay, yeah, we can at least verify whether this works out correctly or not. It is not a universal proof that this approach works in general, but at least you get a confirmation that it is not wrong, at least not in this specific case. So how can we do that?
Test it.
How do we do it? How do we test that?
You can plug in.
All right, so let's work out the other ones, right? Let's work out what is D0. So based on what we have observed, okay, using this as a template, the only thing we're going to change is what the power that we are raising 7 to, but the rest of the structure is going to remain exactly the same. Is that okay? Is everybody kind of looking at this and go like, yeah, that seems kind of obvious because this is for D1 or digit 1, which is the quantity of 7 to the power of 1. This one is corresponding to the number of 7 to the power of 0, right? What about 7 to the power of 2? What about D2? Okay, it's starting to look kind of tedious, right? This is D3, and that is what it is. Are we doing okay so far? All I was doing is to generalize from D1 to figure out D0, D2, and D3, because the approach is the same. It's just that it's a different digit in the number. Are we good so far? Maybe? Kinda? Okay? So now the question is, are we going to do this by hand? I mean, yeah, you can do it by hand if you want to, but it's better to do it using a spreadsheet. Okay? And if you're thinking, but this is a class in assembly language programming, why are we using spreadsheets? It's kind of the same question as, why did you bring a scientific calculator instead of doing everything on a piece of paper? It's a tool, okay? It's just the best tool to get what we need to do done, okay? It's the best tool for the job. So let's go ahead and see, what the tool may look like. Now, if anyone in this class is thinking, but I really don't want to deal with a spreadsheet at all, that's fine. I mean, I'm not going to test whether you know how to use a spreadsheet for something like this or not. It is just that when I need to illustrate the concept, it's easier for me to use a spreadsheet to do the calculation because then I don't have to do it by hand. I'm going to put it into the share folder, so this way you have access to it like right now. Okay, if you want to log into apps.losrios.edu, go to your drive, and then go to this particular share drive. You can get there from the class itself. So if you go to shared folder, which is the second link from course information, you end up at this place. So I'm going to create a new spreadsheet here. So new Google Sheets and create in a shared folder. Yes, that was the intent. And we'll just say this is 1091 in base 7. How's that? I think that should be self-documenting enough so that you know what this document or this spreadsheet is about. All right, so what we're going to do is we are going to start with 1091, which is the number that we want or we're trying to convert, and 7, which is the base. And now we look at the digits. So we have digit 0, digit 1, digit 2, and digit 3. And then over here, we are trying to figure out what D0 is in this case. So do you guys remember how to do this calculation? It's the mod of the floor of whatever value that you're converting from divided by 7 raised to the power of whatever the base of whatever the digit position is. And then you take the mod of whatever base you're working with, which is 7 in this case, like so, and that turns out to be 6. So now I look back into this one and I go, well, anything other than A3, that's A3 here, and then everything else, I need to put a dollar sign in front of the row number, because when I make copies, if I don't put a dollar sign, they will also change at the same time. So the 1091 needs to be stationary because it is giving me the value that I'm converting from. The 7 needs to be stationary and not move along with the row because it is the base. And then the 0 has to float because when I copy this equation to the next cell, it will be working with digit 1 and then digit 2 and then digit 3. So basic stuff about using a spreadsheet. Press the enter key. Now that we have all of those dollar signs in, I can just now replicate the cell to the next 4 cells, and this becomes the base 7 representation of the number that we're working with. Which means, earlier in the conversion, that seems to be wrong, because remember in the text document, I computed this value to be 6. So that means my calculator, I did not use my calculator correctly. Percent probably does not mean mod in that case. Either that, or I make a mistake in the spreadsheet itself. All right, so given that we think this is the base 7 representation of what we know as 1091 is 3116. Because remember, I was trying to check whether the math was right or not. So how do I check it? What was the first thing that prompted us to talk about the sigma notation? What was that equation about? What do you need to know to make use of that equation? And what is it giving you as the result of that equation, of that expansion? Well, let me show you the notes first, and then you guys can try to answer that question. So this is the note, and this is the equation that we are talking about. What does it do? What is B representing? And what are all those D of something? What is B? What is this? We just talked about it. Yep.
It's the digits in what we're converting, like digit 1.
So you're given the digits, you're given the base, and this will tell you what is the value being represented. So the D of something are given to you, B is given to you, and we want to figure out what value is being represented. So that's what we talked about. So now the question is, how do I make use of this to make sure that at least stuff that we talked about is consistent with the new thing that we talked about, which is, given a value, now we want to reverse the process to find out, what each digit is. Go ahead.
Didn't you divide the B value by the base to the index? So like you can do like 1091 and then 3 to the 4th power.
You could do that, but you can also just kind of plug it in, right? Just plug in and say, oh, by the way, we now have a base 7 number. So what we want to do is now to say, hey, this is 6 of 1, this is 1 of 7, this is 1 of 49, and this is 3 of 343. If we add up all of those, do we get 1091 back? Does that make sense? Okay, so let's check it out. I'm going to work on this step by step. So now we're going to say, okay, let's figure out what is 6 times whatever base raised to the power of the position, which is digit 0 in this case. Okay, that seems to make sense, right? 6 times 7 to the power of 0 is just 6 itself. But we also have to remember the base itself, which is B1, needs to have a dollar sign, because otherwise it will, no, this one doesn't, yeah, B1 needs to be changed, because we need to make sure that B1 keeps referring to the base, which is 7 in this case. All right, so we're going to copy this and see if we're doing everything correctly. So what is 1 times 7 to the power of 1? Just 7. What is 1 times 7 to the power of 2? 29, right? What is 3 times 47, excuse me, what is 3 times 7 to the power of 3? Whatever that thing is. So now the question is, when I add up, these specific quantities, do I get the original value back? So now I just say your sum of these 4 cells. Oops, one more. There we go. And we got our original number back. So this is a very quick verification that at least the earlier part of the lecture is consistent with what we are talking about now. And is utilizing things that you have already learned from the earlier part to check to validate the content of a later part of the same lecture. Or if you read ahead of time, you can go through all of this exercise, just prior to the class. Are we doing okay so far? So on one hand, I'm trying to teach you guys the actual content of this class, which is the math behind base conversion. Okay, given a number, given what base we're using, figure out what value is being represented. That's in one direction. But the other direction is, given a value, and I wanted to represent it using a number in a specific base, how do we go the other way around? So that's one thing that I'm trying to teach you. The second thing I want to teach is how to think about all this stuff here. As you're learning, okay, you're not familiar with the sigma notation. In a class, obviously, you can just ask me, okay, because that's why I'm here, okay? That's why you guys are not just reading a book and pay the tuition fee as if you're taking a class. Okay, I hope none of your other classes is like that. You just pay the tuition fee and you open up your Canvas and you just have to do everything by yourself with no interaction with the professor. Because the job of the professor is to answer these questions. Okay, I don't have any earlier exposure to sigma. Okay, fine. We'll just go ahead and explain that. So that's one. But the most important part of what I'm trying to teach you guys is how to use earlier content in the same material to help validate the later content in the same, in the same module in this case. In other words, you are basically giving yourself assignments. Okay, going in one direction, it looks like this, but going in the opposite direction, do I get the original thing back? Because I should. And in this case, this is verification that it is consistent at least. Are we doing okay so far? So that may differ from the way you read material, in high school, because I'm familiar with a lot of people who basically just read the content, in a sequential way, but without really kind of stopping and thinking and then trying to say, okay, this should work. Okay, if I can go in this direction, then I should be able to reverse and get back to the same number that I started off with in the first place. So that's also something that I really try to teach. I'm not sure whether it's working or not, but that's an attempt. Are we doing okay with all this stuff? All right. All right, and that's about it. So now we end up with this notation here. The little thing that looks like a square bracket but missing the top part, that's the symbol for floor. Okay, and can you guys guess what ceiling is going to look like? The other way around, right? Just flip it vertically. That seems to make sense, right? And then we have a mod, basically it's the percent symbol. And this is the general equation, okay? If you want to figure out d of I, which means you're trying to figure out a digit given a particular base that you want to convert to, and also the value that you're converting from, this is the equation to do it. And the spreadsheet already gives you the necessary, name of the formulae that you need to use when you're using a spreadsheet. So if you say, but my calculator doesn't have floor, it's okay. I mean, use the spreadsheet. You guys all have your apps.losrios.edu account, so you can create, any number of spreadsheet that you want. And I really like the use of a spreadsheet because, you can enter multiple formulae in the same spreadsheet and relate the values, of those cells in order to do a complex, calculation. So I always prefer to use a spreadsheet instead of a calculator. Are we good so far? All right. So now, I mean, this is a trivial thing, right? How do we work with binary numbers? How do we convert a value to binary representation? Just make b equals to 2. Then we have base 2. If you make b equals to 16, we have base 16 or hexadecimal. If you make b equals to 10, we have the usual base 10 numbers. That's it. Okay? So if you just read, I'm not sure how many of you actually did, but if you read from the beginning and all the way through, you will see that I'm just generalizing. Okay? I start with something that you are so familiar with. What is 16.375? Tack, are you kidding? Asking this kind of question in the class? But in the process, I'm looking at the structure. I'm looking at the actual structure of what a number is. Okay, what is it? How is it representing a value? Then I generalize using the sigma notation, still in base 10. Then I change the 10 to a b and generalize to any base. And then I use that to reason out the actual equation. And that's it. I mean, that's basically what this module is trying to convey is base conversion. Any questions at this point? All right. So if there are no questions about this module, then we're going to move on to the next module. The rest of this is really just why base conversion or how value is represented in a computer. Why is that important? Because everything in your computer they're all zeros and ones. So just because you know what you want to represent is 169 for example, it's important to know how it is supposed to be represented inside the computer in memory because it is all in base 2 at that point. So number 8 or section 8 is really just giving you an idea of what you can do if you want to get a more in-depth understanding of this material. So you can basically write a C program, okay, or C++, to do base conversion. So write one where you can present a base 10 number because you can use cin to read the number in, and then convert it to whatever base you want to convert it to. So it's from base 10 to base 7, base 5. You can make b one of the variables that you see in. So now your program can deal with just about any base. And then write one in reverse. Okay, give it a number, tell the program what base it is in, and it will give you the base 10 representation. But in either case, you're going to have to perform string processing, look at the digits one at a time, and also plug in the equations that we talk about in this particular module. Are we good so far? So I think that might be a good exercise if you think that you have the time and you want to use that time to help you understand these topics a little bit more. So with this done, and now is a good time to take roll, just because it's right before the beginning of a more heavy-duty topic. So we're going to take roll right now, and you cannot see it yet. Just give me some time to unhide it, and also give you guys, a certain amount of time to do it. I'll give you guys 15 minutes. Nobody walked out of the door, to go to the bathroom right now, so I think you guys can definitely get it done soon. So the answer, let me show you what the answer is supposed to be first. And obviously for people who are watching this but missing and not coming to class in person, and the keyword is Henry. I'm going to put it on the whiteboard so this way you can remember that. And if you guys are thinking, well, that seems pretty random, what is Henry doing, in base conversion? How many people, what do you think? Why do I use, the name Henry for taking row in this case? And I'll give you guys, until 11:30? I mean, that should be plenty of time.
Was Henry the name of the person that developed the...
No? All right, so how many of you have kids or very young siblings? No.
Very young sibling.
Very young siblings? Have you ever watched The Wiggles?
Yeah.
Is it clicking now? Henry the Octopus.
I don't remember Henry the Octopus.
Just random stuff that I remember. So go ahead and take a role, participate in the activity when I look it up. Henry the octopus. There we go. There you go.
Oh.
If you ask me, it is creepy. But that's one of the many characters in the Wiggles.
Wiggles had the hits.
Yeah, the Wiggles have changed a lot too. When I was watching Wiggles with my kids, it was only like the four dads.
Yeah.
Now they have younger people instead of the original four dads. They got old. They got.
In their 50s by now.
Oh yeah, I mean yeah, yep. Because I was watching this with my daughter 20 years ago. Just as I have aged, these guys would have aged as well, and that's why it's a smart thing that Barney is always you can never tell who's inside the suit, right? The costume. Yep, that's Henry. That's why, because we were talking about octopus too. That's basically how my brain works. Just kind of random, really, really random firing at times. All right, so I'll be good with road taking. Has everybody participated in the road taking activity? So now we're going to start with binary addition. We are going to add numbers in base 2. And this is where things start to get a little bit like, there's a lot of stuff in here. So at this point, I'm hoping that you guys are definitely starting to consider taking notes. Okay, not just during the lecture, but also read a little bit ahead of time. Take your notes, and then come to the lecture, take some more notes, and then go back and review your notes, and then put all the definitions, all the symbols in the one little corner, so that way it's easier for you to locate the definitions, because there are lots of definitions here, and if you don't track the definitions, it's going to be hard to find. Okay, they're difficult to find. Not that I intentionally make them difficult to find. It is just that there are just a lot of stuff. All right, so we're going to talk about adding in general, and I'm going to do one example. I don't think this is really important that you capture it in your notes. Not so much the numbers themselves, but the method. Okay, so I just want to present to you a multi-digit addition in base 10. Okay, something that you should be able to do, like tech really in a class like this. All right, so we'll go ahead and start with, I'm just randomly picking some numbers, 476, and we're gonna add to it, maybe 327, okay? So I do have to say this, without, being, not intending to be judgmental, but if you cannot handle this math here, your programming may not, taking this class may not be a good choice. Okay, I'm just going to say that. And, I'm saying that not so much as a joke, but and also not to, be judgmental because, there's going to be a lot of math stuff in this class. This is really just kind of the beginning. So normally how we write this is, 6 plus 7. What is 6 plus 7?
13.
It's 13 or 3 with a carry of 1. So the way we want to look at this is it is 3 with a carry of 1. And then you guys say, but this is not how my high school or elementary school teacher used as a format. Just bear with me, okay? I use one row for the result of the addition, and then one row specifically for the carry. So the carry of 6 plus 7 is on the next column because it is indicating the value of 6 plus 7 can no longer be represented by a single base 10 digit. So instead, I'm going to say, this value is way too much for a single digit to handle. What about you? Okay, digit 1, you handle the 10. I will just handle whatever is left over, which is guaranteed to be within the range of 0 to 9. Okay, so at this point, we just assume a zero here, which means the carry to digit 0 is assumed to be 0. It doesn't have to be as we move on, but at this point, we just say, we'll just assume a 0 there. All right, so instead of completing column 0, now I choose to do it in a very slightly different way. Now I ask, what is 7 plus 2? 7 plus 2 is 9. with a carry of 0 at this point. But I'm not going to put a 0 here, okay? And then we have 4 plus 3, which is a 7. Okay, so now we look at 9 plus 1. What is 9 plus 1?
10.
We can call it 10, but in a multi-digit addition, we can call it a 0 with a carry of 1, right? So we have a 0 with a carry of 1, and now we can we can complete this in random order. We can now say, what is 7 plus 1? That's an 8. What is 3 plus 0? It is just 3. All right? So now we look at this addition and go like, yeah, so what is the big deal, right? What is the big deal? Well, the big deal is we have two concepts that are very important. 6 plus 7 having a value of 3 is what I would call the single-digit sum of addition. Now, I'm not really sure whether there's a technical term for that, but I just call that the single-digit sum of 2 digits. Because 6 plus 7 is technically 13. But if I want to look at that value and say, okay, if I just focus on one single digit, what is it? It's 3. This is the carry of 6 plus 7. 6 plus 7 has a carry of 1. Okay? 9 plus 1 also has a carry of 1. 7 plus 2 has a single-digit sum of 9. 9 plus 1 has a single-digit sum of 0. And then 4 plus 3 has a single-digit sum of 7, and so on. So are we doing okay so far with, just naming the various parts of this thing? All right? So now the question is, okay, this is a concrete example. How can I generalize this, okay, and say, okay, so in general, base 10 addition is like this, da, 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 da. So it looks like we got two things to handle. One is what is the single-digit sum of blah and blah, and then the other one is what is the carry of blah plus blah, right? So now we want to look at those. I mean, all I'm talking about now, they are all in the notes already. So if I use C as a function, this is actual C code. So if I want to find out what is the carry of a single digit x plus another single digit of y, I can use this particular C function. Okay, so let's take a look at the C function and make sure that we understand it. Because you guys have all taken CISP310. I checked, okay? And this is something that you should understand at this point. Some of you may look at this and frown a little bit because your professor may not have introduced what we call the ternary operator. But that's okay, I'll explain that as well. So the first thing is we compute the sum of x and y. And if it is greater than or equal to 10, then we got this really kind of strange symbol here, which is a question mark. And the question mark is always paired with a colon in a ternary expression. So does anyone want to help me explain what does it mean? What does this expression mean when you need to evaluate the value of that expression? So let me just highlight what I'm trying to talk about here, and you guys can give me the answer. Go ahead.
If x and y are greater than 10, return 1. If it's less than 10, return 0.
Exactly. So it's basically if, then, else in a single expression. The first part, which is to the left of the question mark, is your condition. Just like the condition of a conditional statement. Whatever is between the question mark and the colon is what I call the then value. So if the first expression is true, then the then value becomes the value of the entire ternary expression. On the other hand, if the condition is false, then whatever is to the right-hand side of the colon becomes the quote-unquote else value, and that becomes the value of the entire ternary expression. In other words, it really is if then else as a single expression. So by using a ternary expression, I can now use a single return statement to do what I need to do. Because the bottom line is if x plus y is greater than or equal to 10, then the result can no longer be represented using a single digit, and we have a carry of 1. Otherwise, if x plus y is less than 10, that means I can still use a single digit to represent the entire sum, so we don't have a carry of 1. We have a carry of 0 in that case. All right, next question. Why do we need to do this? Why don't we just say x plus y is greater than or equal to 10 without the question mark and the colon, without the ternary expression? Is the ternary expression really necessary? So that depends on how you were taught about how Boolean values are represented in C++. If your professor is like me, to basically go all the way to the standard and say, well, in C and C++, this actually means true, not what you think, what you might think, and this represents 0. So let me ask you that question. What represents true in C and C++? Go ahead. One is one of those things, yes. One is definitely considered as true, but what is the most general way to describe what is true in C and C++? Go ahead.
Anything besides 0?
Exactly. Anything other than 0. So that means 2 is also true. 3 is also true. Negative 16 is also true. 3.14 is also true. Hey, this pointing to that location that is not null is also true. True itself is true. Okay, if you're using C++, that's actually a bool type. So if I don't use this ternary operator, there's no way for me to actually know what it is going to return. We just know that it's going to return a non-zero. But it's kind of troublesome if you just return a non-zero when you're trying to do some calculations, right? So that's why I need to use a ternary operator to make sure that what it returns is either a 1 or a 0, because I don't want it to return a 2 or 22 or negative 5 or pi. Okay, I really want it to just return a 0 or a 1. Are we good so far? All right. What about the next one? The next one is what I called earlier as the single digit sum between two digits. So we make the assumption that x is a single digit, y is also a single digit, in this case in base 10, and we want to figure out what is the single digit sum between digit x and digit y. Basically, if x is 6, y is 7, we want a value of 3. Is that okay? Does everybody now understand what R is trying to compute as a function? Okay, well, it's not that hard. I mean, if we know ahead of time this is in base 10, then all we need to do is to compute the sum between x and y, and then just mod it with 10, and then we end up with the single digit sum of x and y. Are we good so far? So are we making a okay transition between the example, the concrete example, and the C functions that are used to compute the single digit sums, and also the carries? So we good so far? So now we make it more general, because we want to look at the concrete example and then use that as a way to generalize so that we can now extract the structure of how we perform multi-digit addition. In other words, if you are to teach an elementary school student how to perform multi-digit addition, how would you do that? You cannot just show one example and go like, oh, I think you guys are good, okay? Because they can just remember one single example, right? So you have to show them the structure and go like, okay, regardless of what digit is, regardless of what this digit is, this is always going to be the single digit sum between those two digits, okay? So from here on, I'm going to name the rows, okay? Each row now has a name. You don't have to write it down because it is in the notes or in the module already, but it also means that you might need to read the module in a careful way and find all the definitions, okay? How do I name different things? Because I need a way to designate and say, I'm talking about this digit here. What is the name of that digit? So the rows are called X, Y, Q. Need to mute my phone. Sorry about that. This is Q, this is K, and this is S, okay? That's how the rows are numbered. And then the columns are numbered 0, because it's digit 0, digit 1, and digit 2. So are we doing okay so far? This is just how I name the various parts of a multi-digit addition. All right? So the x and the y's are given. Those are the things that you are given with, along with k0. K0 is always a 0, but you can just consider it as given. So we need to figure out the rest. That's what we need to do, is to figure out the rest. Okay? So now I erase the actual concrete values and replace those things with names. Okay? This is x0, this is x1, this is x2, this is y0, this is y1, and this is y2. The module contains the same information but may not be presented the same way. So if you want to take a picture of the whiteboard at the end of the class, that's fine too. Okay, that's up to you. So now we look at the 3, the 7, 9, and the 3, and go like, what are those things? So if I just say, okay, erase these and just rename them to Q0, Q1, and Q2, do I know how to compute Q0, Q1, and Q2, given all the x digits and all the y digits? Can I generalize? If I say not even a specific Q, and I just say, if I want to figure out what is Q of I, how do I compute it? I being the position of the digit. So what would be the equation to do that?
Would be x naught plus y naught mod 10.
Okay, so using the function that we have already defined, is there a way to use C or R in some way? Which one would I use? The Q's are the single digit sums, right? So there'll be R. Okay, the R of what? Remember the 3 is the 6 plus the 7, but it's the single digit of 6 plus 7, right? So the 6 was x0, the y was y0. And then the 3, which is the result, was q0. So if I just generalize the position of the digit, what should I put here? xi and yi. Exactly. So we have xi, yi over here. Is that okay? So you can see, so this is where it gets tricky, because I'm trying to generalize, I'm trying to abstract and move from a concrete example to equations. So this way I can just say, hey, I goes from 0 to 2, but regardless of which value, 0, 1, or 2, this is the format, this is the structure. This is how we compute the digits of the Q row. Is that okay? All right? So now we look at the k's, okay? So now I say, what is ki plus 1, which is the k of the next column? How do I express that? So what we want to do is to look at 2 of the carries. So let's focus on this carry first, okay? The carry that was the result of 6 plus 7 is greater than or equal to 10, okay? So with that one, what would be at least a component of k of I plus 1? So we need to use C because it's a carry. So let's start with the C. And what do we put inside what do we use as arguments? Xi, yi. Very good. Okay, so this is really important because this is ki plus 1, but in order to compute k of I plus 1, we are only using xi and yi. So they're off by one column. Okay, the result is this column, but what we use to compute that is the previous column. But that makes sense because the carry is telling you whether we have a plus 1 on the next column or not. Okay, so that handles 1, but look at this one over here. This one was because of a 9 plus 1. That's not x and y, that is between q and k, right? So what is the other component to compute k of I plus 1?
Q at I plus 1 and...
Well, think about this. What is the name of this guy? If I were to use the row name and the column number, what would that be?
K2.
It's K2, right? So K2 relies on Q1,
Q1.
K1. So once again, the index is off by 1. So now we have Qi, Ki. So we know there are two ways to end up with a carry of 1. It can be because the x and the y added together being greater than or equal to 10, but it can also be because the q and the k adding to a value that is greater than or equal to 10.
So the K's, the index for the K's are up. They're like the set above the
It's
I.
the one before, right?
So then everything else you refer to inside the parentheses is working with I.
Right. So if I were to use a different color to indicate the path, this one here can come from this addition, but it can also come from this addition here. All right? This K here can come from these two added together, can also come from these two added together.
Okay.
All right? Well, I just gave you the answer, but I'm going to ask you the question now. I know it has these two components, but how should I combine these two components?
Addition.
Addition, okay, so we have addition here. Okay, that's fine. I'm just using a line to separate between these two parts. So now we basically have a question of, okay, so far so good. We'll just use a plain addition here. But when you use an addition, and you look at this example here, it really begs the question of, is it possible that this is giving you a 1 and this is also giving you a 1? You end up with a carry of 2. Is that possible?
No,
And why is it not?
because you can, given two numbers, like if you're trying to get, say for example, if you're trying to get to 20, but you can't ever get to 20 with just two single digits, because at the greatest you can have 9. So 9 plus 9 will always be 18.
But what about that carry?
Or what about it? The 1 goes over, but then it's never gonna send 2 over.
Mm-hmm. But why can't both of these carries be 1s at the same time? We see one chance where the QI, 1 is 9 and 1 is 1, and we end up with a carry of 1. We saw in the other case where Ki is a 6, and the Yi is a 6. 1 is 6 and 1 is 7, and we still end up with a carry of 1. So the question is, why can't we end up with both carries being 1s? Okay, so I'm trying to show you the reasoning now, okay? You have a very strong suspicion that it's not possible, okay? But a suspicion is not a proof. It is not definitive. You cannot just say, it just seems like that way, okay? That is not going to be a mathematical proof. So now the question is, now you have to think about the scenarios. And you also have to go back to the definitions, okay? So this is one thing that I cannot overemphasize is when you start to think about how to solve a problem, you have to understand the problem from the perspective of the definitions. Try to fit the problem into the terminologies that you have been introduced already. So what we know is this is Q of I, okay? So let me try to explain that using the text editor, because I think this way I don't have to repeat the whole thing. So I'm going to use just K of I plus 1 equals to C of X. Okay, is it okay for me not to use the bracket, because that's just a lot of typing? Okay, so it's kind of implicit that this is Xi is in bracket or subscript, yi plus C of Qi Ki. Okay, so this is capturing what we have on the whiteboard already. The question is, can both Xi yi, the carry of Xi yi, and the carry of Qi Ki both be 1s? And the answer is not, it is not possible. But the question is, why is it not possible? Okay, so now we say, C of Qi Ki equals to 1 if and only if there's only one case that this can happen in base 10. The only one case is Ki has to be a 1 and Qi has to be a 9. Does that make sense? Now, based on the assumption of Ki cannot be more than 1, this would be the only case that can cause that to happen. All right? So now we look at this and go like, yeah, so what is the big deal? What is Q of I? Look at the definition of Q of I on the whiteboard. Q of I is R of xi yi, right? So this is R of xi yi. And what exactly is R of xi yi? What is the definition of R? Well, we saw that earlier in the browser. Okay, it's still right here. Okay, it is x plus y, mod 10. All right, fine. So you just expand it. It becomes xi plus yi, the whole thing mod 10. What is the big deal here? I don't see what is the big deal. So why can't Q of I be 9? Because if Q of I can be 9, then we end up with a case where both carries are contributing ones at the same time. So you look at this and go like, I don't see how it cannot happen. But that's because we have one extra constraint. So when you think about problem solving, you also have to remind yourself of all the constraints. The constraints in this case has to do with xi is a single digit in base 10. Yi is also a single digit in base 10. A single digit in base 10 can go from 0 to 9. Exactly. So xi can only go up to 9, yi can only go up to 9, which means the largest sum you can get in the addition by itself is 18. And the 18 mod 10 is 8. You cannot reach 9. So there you have the issue. Okay, so that's the reason. So then somebody's going to say, but I can still generate, R of xi yi being, 9, because I can just say, one is 4 and one is 5. Yes, you can. But in that case, C of xi yi is going to be a 0. So when R of xi yi is 9, C of xi yi has to be 0. Am I doing okay so far with that? Let me just write it down, and you guys can ponder upon this for a little bit. Okay, so I'm saying if R of xi yi is 9, then C of xi yi is guaranteed to be a 0. And I can also guarantee if C of xi yi is a 1, then R of xi yi has to be less than 9. Okay, so just in terms of arithmetics, okay, try to reason that out, okay, in your head. But the bottom line of these two statements is the two C's cannot both be 1s. Up to 1 can be a 1, but they cannot both be 1s. Can they both be 0s? Yeah, easy. They can both be 0s, not a problem. They just cannot be both be 1s. All right? Wait. If this is what you're saying, okay, so let's just say that I'm using A to represent C of xi yi, and I'm using B to represent C of qi ki. So in terms of a table, okay, we have column A and column B. You're basically saying 0 0 can happen, 0 1 can happen, 1 0 can happen, but 1 1 cannot happen, because the two contributors of the carry cannot both be 1s. Okay, all right, so we now look at A plus B. 0 plus 0 is just 0, 0 plus 1 is 1, 1 plus 0 is 1, and this one is, it does not happen, okay? Never happens or not applicable. Okay, and remember, how we are kind of obsessed, how I am kind of obsessed of getting things done using transistors, right? That's one obsession that's going to go all the way to the end of this semester, is how do we do this in transistors? Okay, so you look at A plus B and go like, oh, that's an arithmetic operation. We cannot do that using just transistors, or at least tech has not taught us how to perform addition using just transistors. But we have something that's close. Okay, so we have A or B, right? We have already established that the regular logical OR can be done in transistors. Just use a bunch of NAND gates, right? And each NAND gate can be done using 2P and 2N transistors. Okay, so let's flow with this for a little bit and see where this is going to go. Okay, 0 or 0 is a 0. 0 or 1 is a 1. 1 or 0 is also a 1. But then someone is going to say, but A plus 2 1 plus 1 is a 2, and then 1 or 1 is still a 1. I don't care because that condition never happens. A and B cannot be ones at the same time. So I still just write down not applicable here. So in this very specific case, whether I use a logical or whether I use an arithmetic addition does not matter.
Is that why the symbols are the same in or in discrete manner for or?
Sort of, yeah. It's that has to do with abstract algebra. So they have similar properties from an abstract sense. So addition is kind of like or, and then multiplication is kind of like and. So you can still use distributive law, you can still use commutative law, and all kinds of other laws, with only those operators. One has an identity of 0, addition and or they both have an identity of 0 or false. Because 0 plus whatever is whatever. False or whatever is whatever. And then the other one has 1 as an identity. In other words, 1 times whatever is whatever, and then true and whatever is also whatever. So from a very abstract sense, they share certain properties, and that's why we sometimes interchange the signs or the symbols. So what this table is telling you is, so in this very limited context, I don't really need arithmetic addition. I just need OR, which I already know that I can do it using transistors. Okay, so we have solved one little mystery at this point. So that means I can now go back to the original calculation of C and Ki plus 1 and replace this with a logical OR. Now, obviously, we still have some problems, right? Because we still have the problem of how C and R are defined, okay? At this point, C and R are defined that they have to use addition and comparison, which we don't know how to convert into transistors. Not yet, right? So I know we are running out of time for the lecture. On Wednesday, we're going to move on and talk about base 2, okay? How do we add numbers in base 2? Just based on what you're seeing on the projector right now, what do you think is the easiest way to say, oh, we get it, it's not a problem. We just have to change this to that, and now we have base 2 addition. What are you going to do? Look at what you're seeing here.
Change the 10 to a 2.
Yes! Change the 10 to a 2, and now you have the carry function and a single-digit sum function for base 2 addition. And then you go like, but Tag, that's not helping in the sense of we still need addition, right? So that's a mystery that we're going to solve on Wednesday. For those of you who are going to read ahead of time, please do. For those of you who say, but if I read ahead of time, I lose my curiosity and I'll just fall asleep in class. Well, then pay attention in class on Wednesday because I'm going to give you that answer of how we can do everything using transistors, even though we're trying to deal with addition now. All right? So with that all said and done, let me open up the lab. You guys can go take a break before you start with the lab. All right. So the lab today is going to be pretty easy to do. I will put the passcode or the access code on the whiteboard, so when you guys come back, it's still going to be there. It's about base conversion. There are only 4 questions, so it's an easy one to do. The access key is arrival because of the movie, because they have all those heptapods. So arrival is the access key, and you have until 1:20 to do it. So let me put down 1:20 as your due date today. And there you go. Go take a break. When you come back, you can start, or you can just start now if you don't need a break. It's up to you guys.
Apparently there's a car on fire
A car on fire
in the 2nd floor
of the parking lot.
That's what all those calls were for.
Oh.
I got like 4 calls.
Wow. I only got one.
Whose car is it?
I don't know.
Phoenix Rose. Hopefully.
I didn't park there.
Which parking lot?
That would be the parking structure.
Over there.
Yeah, we only have one multi-story structure.
Yeah.
Was on fire?
Yeah. It was on
Whoa.
fire.
It was just like you were just saying it earlier, but it's sinking in right now. I was like, that's pretty.
That's pretty wild.
Yeah.
Crazy.
Watch it be a test.
I mean,
Actually, it's not as crazy as you guys may think. Let me turn off the